Hello, good morning everyone. Let's begin with today's session. In the last few sessions, we have seen the basic relational algebra operations. So we have gone through 6 basic operations such that the select operation, project operation, set difference operation, union operation, rename operation and Cartesian product operation. So these 6 are the relational algebra operations. Those are basic. Apart from the basic relational algebra operations, we are having few additional operations as well. So what are those additional operations and why these operations are being proposed? So we define these additional operations that actually do not add any power to the relational algebra. I'll repeat, the additional operations do not add any power to the relational algebra. But these additional operations are meant for simplifying our task. So many times it happens that even though the basic relational algebra operations can be used to write the query or perform the task, these queries become a bit complex. So to simplify writing the queries, we have come up with few additional operations, and these operations are not adding any power, meaning whatever we can perform by means of these operations, all those things can be performed by using the basic relational algebra operations, no doubt. So we are not at all adding any power to the relational algebra, but by making use of these additional operations, it is possible for us to simplify writing the queries. So what are these additional operations? Those we are going to focus upon. These operations are set intersection operation, then the natural join operation, the assignment operation, and the outer joins. So we are going to focus upon these additional operations now. So let's begin with set intersection operation. So we have seen the union operation earlier. The union operation is the basic relational algebra operation, and the set intersection operation is the additional operation that is providing us simplified way to write the queries. So the notation used for intersection is this intersection symbol. So we write R intersection S, where R and S are the relations. Okay, R and S are the relations. And this set intersection operation requires two operands or two relations, and this is how this intersection operation is the binary operation. So how to define this binary operation intersection? We say that R intersection S is giving us the set of tuples T such that T belongs to R and T belongs to S. I'll repeat. Set intersection operation can be defined as a set of tuples T such that T belongs to R and T belongs to S. If you remember our union operation, the definition of union operation was similar, except this AND logical operator. Instead, we mentioned there OR in union. So here in intersection, we are saying that it is providing us the set of tuples T such that T belongs to R and T belongs to S. Once again, we need to satisfy two conditions here. R and S should have the same arity and attributes of R and S must be compatible. Then and then only it is possible to have the intersection operation. This intersection operation, as I stated, this intersection operation is the additional operation and it is not providing or adding any power to relational algebra. Only it is trying to simplify the things. So this intersection operation R intersection S can be written by making use of the basic relational algebra operations like R minus S. So this minus is nothing but set difference operation. So we may write intersection operation using the set difference operation, which is a basic operation. So R minus S is nothing but R intersection S. We will see one example for that. So let us assume that we are having two relations R and S. R is having two attributes A and B. Also, S is having two attributes A and B. These two are the instances of R and S. Now, if we want to write the resultant relation of which is the outcome of R intersection S. What is the outcome of R intersection S here? If R and S are given as shown, what is R intersection S? It will give us the set of tuples
alpha 2.
Yes. So it will provide us the set of tuples such that tuple T belongs to R and also it belongs to S. So we need to pick the common tuples in both the relations, right? So this will provide us the answer as alpha 2. Now, as I stated, this intersection operation can be written by making use of the basic relational algebra operation. So, how we are going to do that? Let us try to find out R minus S. So, what would be the output of R minus S? Set difference operation. R minus S, what would be the output?
Alpha 1, beta 1.
Yes, correct. So we are having alpha 1, beta 1 as the output of our set difference S. Right? And now if we try to compute R minus S, then what would be the result? What is R? R is this given relation. And what is R minus S? We are having computed this relation R minus S. And now we want to have a set difference between this R and R minus S. So what would be the result?
Alpha 2.
Alpha 2.
Alpha 2. Yes, correct. Alpha 2. So this is how we can prove that this R intersection S is equivalent to R minus S. Right? Any doubt so far? Yes? Any doubt so far? May I proceed?
Yes, ma'am.
Yes, ma'am.
Fine. So let us try to write now one query based upon our university schema. Find the set of all courses taught in both the fall 2009 and the spring 2010 semesters. Earlier we have written a similar kind of query if you remember. using the union operation. Do you remember how we have written those queries? We have written a query like find the set of all courses taught in fall 2009 or spring 2010 or both. Correct? And now what we are writing? We are writing a query find the set of all courses taught in both the fall 2009 and the spring 2010 semesters. So what we need to do? Once again, we need to split our task such that we can extract the courses those are taught in fall 2009. Also, we need to write a query such that it will extract the courses those are taught in spring 2010, and then we need to pick the common tuples by making use of set intersection operation. Do you agree with me?
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
So now simply write the query. We have written the partial queries earlier. So you are supposed to reproduce these partial queries, and simply you need to make use of intersection operation to come up with the final result. So which relation to be used?
Section.
Section relation. Yes, correct. Section relation to be used. And we have already written the partial queries earlier. So section relation to be used, and with this select operation with the predicate semester equal to fall and year equal to 2009, it is possible to extract the data satisfying fall 2009. But out of all those attributes, we are interested in only the course ID, and that is why we are making use of this project operation with course ID. So this is our first part of the query that will provide us all the courses those are taught in fall 2009. Similarly, it is possible to write the query to extract the course ID from section table such that those courses are taught in spring 2010. And what we are asked for, we want to extract all courses taught in both. So what we need to do is we need to pick the common course IDs from these relations, and that is why we are making use of the intersection operation. Right? Am I correct? Yes? Any doubt so far? Is there any doubt?
No, ma'am.
May I
No,
proceed?
ma'am.
May I
Yes,
proceed? Fine.
Yes,
Yes,
ma'am.
ma'am.
Okay, thank you. So let's proceed now. Next additional operation, very important operation, and that is the natural join operation. So let us try to explore now this operation. The symbol of the notation that is being used for natural join is like this. This is called as a join symbol. Once again, this natural join is a binary operation and that requires two operands or two relations. So we are reading this operation as R natural join S. Okay. Now, let us try to define this operation of natural join. Let us assume that we are having these two relations R and S on the schemas capital R and capital S respectively. Okay, and now we are going to define this natural join of R and S. So the natural join of R and S will provide us a new relation with the schema R union S. I'll repeat, the output of our natural join S will provide us a new relation on schema capital R union capital S. And the formal definition of this natural join operation will look like this. So what we have here, please listen carefully. We are defining the natural join operation in terms of the basic relational algebra operations. So if you look at this basic relational algebra operation or the expression written using only the basic relational algebra operations, you may find that this expression is a bit complex expression. So this entire thing can be compressed in the additional operation that right now we are defining and which is known as a natural join. So as we have stated, this natural join operation is having the schema R union S. R union S. So we are defining this operation as the project operation with R union S. So R union S will provide us the list of attributes, right? This R union S will provide us the list of attributes. What is R? R is the schema on which this relation R is defined. What is capital S? Capital S is the schema on which this relation S is defined. So our natural join S is defined on the schema R union S. So we are writing here the expression as the projection on R union S. So this will provide us the list of attributes. Now this project operation is performed on another relation, and what that relation is, this relation is defined as this expression by making use of the select operation. So select operation on R cross S. So we are having here the Cartesian product of R and S, right? And see here carefully what we are trying to do. This R and S are having few attributes, those are common. Few attributes, those are common. So we are having a predicate on R cross S. And what that predicate is, whichever are the common attributes in both R and S, we are matching the values of the common attributes. So our predicate in this select statement is like R dot A1 equal to S dot A1 and R dot A2 equal to S dot A2 and so on up to R dot AN equal to S dot AN. So what are those A1, A2 up to AN? These are the attributes. Those are common to both the schemas R and S. So whichever are the common attributes in R and S, we are trying to match the values of those attributes. Right? So this is how we are going to define our natural join operation. So let us see one example to clear the idea. So let us assume that our schema capital R is given as the attributes A, B, C, D, and the schema S is given as the attributes E, B, D. Right? So the operation should have the schema R union S. So what is R union S? In this example, R union S. Yes? Anybody? What would be the R union S schema? Yes.
A, B, C, D, E.
A, B, C, D, E. Yes. So my natural join relation will have this schema defined as A, B, C, D, E. That is R union S. Okay. And now, according to our definition, how we are getting the result? Just look at it. We are writing this natural join operation as the projection operation on the list of the attributes given as R union S. So here R union S is our resultant schema, right? So we should have all those attributes listed over here, A, B, C, D, E. Now, from where we are getting this A? A belongs to relation R. So R dot A, B belongs to both, right? But we need to specify from where we are getting that, right? So we are mentioning R dot B, R dot C, R dot D, and E belongs to S only. So we are writing S dot E, right? So this is now giving us this R union S, all the attributes in R and S, right? And the common attributes will appear only once because it is union operation. Okay, so the common attributes will appear only once in natural join. Okay, now we are going to extract these attributes from both R and S. So how we are going to write the next query? We'll be having the Cartesian product of R and S, so R cross S, and we are having the selection operation on the result of R cross S with the predicate. And what that predicate would be? The predicate is written on the schema R intersection S. So which are the common attributes in R and S? What is R intersection S? R intersection
B
S.
and D.
B and D. B and D. So these two are the common attributes. Those belong to R and S, right? So we are writing the predicate such that we want to equate, we want to match the values of the common attributes in R and S. So our predicate will become like R dot B equal to S dot B and R dot D equal to S dot D, right? So we are computing the cross product and the result of cross product will be imposed with the predicate such that the common attribute values are matched, right? So we are making use of select statement to impose the condition, right? And whatever are the results, whatever are the attributes in the result, we want to pick only the attributes from R union S, right? So we do not want to duplicate any column. Please remember, we do not want to duplicate any column. So even though B and D are there in both R and S, in our final output, B and D will appear only once. Got it? If you have any doubt, please let me know. This is really very important operation and this operation is really very handy. So instead of writing the complex queries, by making use of natural join operation, it is possible for us to simplify our task.
Yes, ma'am.
Yes, ma'am.
Okay. So let's see now one example of natural join. So let us assume we are having this R instance of relation R with the schema capital R equal to A, B, C, D. And we are having this instance of relation S on the schema capital S equal to B, D, E. Right? So here this R is nothing but these attributes are A, B, C, D, and this capital S is the schema having the attributes B, D, E, and these two are the instances of the relations R and S on schema capital R and capital S. Okay, now to compute this natural join of these two. Natural join of these two. So, now please tell me what are the attributes of our natural join S? With the schema for the resultant relation?
Capital A, capital B, C,
Yes.
D, and E.
What would be the schema for our natural join S? A, B,
C, capital D, and capital E.
so the schema for our natural join S would be capital R union capital S. Correct? Na? So we know the schema capital R, we know the schema capital S. So schema for our natural join S would be R union S, capital R union S. So we'll be having 5 attributes A, B, C, D, E in our output. Correct? Now, according to our definition, what we are going to do is, we are going to find out the cross product R and S, and we are extracting only those tuples from this cross product those satisfy the condition R dot B equal to S dot B and R dot D equal to S dot D. So we are having two attributes common, B and D. So our intersection S has two attributes B and D, those are common. So what we need to do is, we need to match the values of B and D in both the relations. In cross product, what we have is, we are having all the pairs of all the tuples in R and S. So in my R cross S, how many tuples I will be having? In R cross S, how many tuples I will be having? In the Cartesian product of R and S, how many tuples?
25.
25, because this relation R is having 5 tuples and this relation S is also having 5 tuples. So 5 into 5. So R cross S will have 25 tuples. Now, what we are doing is, on this result of 25 tuples, we are putting a predicate. We are imposing a predicate such that we want to match the values of common attributes. So, let us look at which are the common attributes here, B and D. So we want to match those values. So B and D 1A, here B and D 1A, here B and D 1A. Correct? So with this alpha 1 alpha A, we are going to match the tuples. So in cross product, for this first tuple, I'll be having pairing of all those 5 tuples. So in cross product, I'll be having alpha 1 alpha A 1a alpha, alpha 1 alpha a 3a beta, alpha 1 alpha a 1a gamma, alpha 1 alpha a 2b delta, alpha 1 alpha a 3b epsilon. Right? So in cross product, I'll be having for this first tuple of R 5 pairings as I stated. Okay, out of those 5 now, which tuples we are going to select? We are going to select only those tuples for which B and D values match. So how many tuples are having B and D matching with 1A? 2 tuples. So we'll be having alpha 1 alpha A alpha and alpha 1 alpha A gamma. Because this 1A are common, we are not going to repeat those columns, right, in our natural join. So in our output, we'll be having alpha 1 alpha A alpha, alpha 1 alpha A gamma. Because
Hello,
for
ma'am.
this, yes,
Ma'am, some of us haven't understood this natural join operation. Can you explain once again from start, please?
okay. So have you not understood the definition?
No, ma'am.
Okay, so let's go back. So we are having the definition for natural join as shown over here. So as I stated, natural join is the additional operation, and this operation is actually been written by making use of the basic relational algebra operations, right? So to write the natural join operation, we are making use of 3 basic relational algebra operations. What are those 3 basic relational algebra operations? We are having the cross product, we are having the selection operation, and we are having the projection operation. So combination of these 3 operations will provide us this natural join, our natural join S. Right? If you remember our earlier discussion with respect to the Cartesian product, we stated earlier that if we compute the Cartesian product of 2 relations, it happens that few of the tuples in the Cartesian product are irrelevant. Do you remember this discussion? Many students were absent in the last session, and I guess due to not understanding the earlier discussion, you are not able to understand this operation of natural join, because natural join is based upon the Cartesian product. In the last discussion, we stated that whenever we compute the Cartesian product of 2 relations, it happens that few of the tuples in the output of Cartesian product are irrelevant. And the reason was, in Cartesian product, we are having all the pairings of the tuples from R and S. So we do not have any logic to match the tuples in Cartesian product, and that is why we are having the huge relation comprising of the number of tuples equal to the product of number of tuples of R and number of tuples of S. So simply we are having all such pairings in Cartesian product, but some of the tuples in Cartesian product are irrelevant. And what is the reason? Let me give you one simple example once again. If I am having two relations, say R and S, and these two relations are based on, say, attributes of R are, say, A, B, C, and let us assume simply the attributes of S are A and D. Let us assume that we are having A, B, C as 1, 2, 3. Let us assume this is one example only. Then another tuple that I am having is, say, 2, 4, 1, or rather I'll go to Excel once again to demonstrate this. Let us assume that we are having capital R as A, B, C with 3 attributes. Capital S is having 2 attributes, say A and D. And we are having 2 instances now of relation R on R and S on S. So this is my relation R on capital R, and this is the relation S on capital S. So the attributes of R are A, B and C, and the attributes of S are A and D. Let us populate these two relations randomly. So suppose we are having the values of ABC as 1, 2, 1, 2, 4, 3, 3, 5, 1, something like this. And we are having another relation S with the instance like 1, 4, 2, 7, 2, 2, 3, 4. So these are 2 instances of R and S. Okay. So if we want to compute now the Cartesian product R cross S, R cross S. Compute the Cartesian product of these two relations. What are the attributes in our Cartesian product? Yes, anybody? What are the attributes of Cartesian product?
M plus N.
M plus N. Yes, right. So if we are having these two relations R and S, the attributes of R cross S would be A, B, C, A, D. Correct? So A, B, C are the attributes from R and A and D are the attributes from S. So in our Cartesian product, R cross S will be having these 5 attributes A, B, C, A, D. And how we are going to populate? How we are going to populate this R cross S? According to definition of R cross S, we are having all the pairings of the tuples from both R and S. So I am having this first tuple R and that gets paired with correct? Are you getting me?
Yes.
Right? So these are actually the tuples from S. So this first tuple from R gets paired with all the tuples from S. So we'll be having 4 such tuples now. Right? Similarly, this second tuple R gets paired with all 4 tuples from S. Do you agree with me?
Yes,
Yes?
ma'am.
Yes, ma'am.
Okay. So these 4 tuples once again. Now, for this third tuple in R, we are having pairing with all the tuples from S. So once again 4 tuples we will be having. Right? So how many total number of tuples we will be having? 3 into 4. So 12 tuples we should have. Right? So we are having those 12 tuples in our R cross S. But if we look at these tuples, those are there in R cross S. We are having the common attribute A. We are having the common attribute here, that is A. A is common in both. Right? So whenever we are having the matching values for the common attributes, only those tuples are actually the relevant tuples. And if in a single tuple, if for the common attribute, if I am having different values, then these tuples are not relevant. So if you remember, we had a discussion in the last session that along with the cross product, we need to provide the predicate to match the values of common attributes. Then only we are getting the result which is relevant. Right? So on this cross product, we need to apply the condition such that the values of common attributes are same. So what condition we should apply here? What condition? We should apply here the condition that the select statement will be having the predicate such that R dot A equal to S will be having the condition like R dot A should be equal to S dot A because A is my common attribute. So I need to have this condition on the product R cross S. Then only it is possible for me to get something relevant. Otherwise, there are few tuples. Those will give me some irrelevant data. Irrelevant data that is not expected. Okay. So to do next is we are going to apply the predicate. So A is the common attribute in both. So we are going to match now the values. So if we look at this first tuple in R cross S, then whether R dot A equal to S dot A, R dot A equal to S dot A, yes, that is true. So we need to pick this tuple. Now, for this, whether R dot A is equal to S dot A, no. So we need not pick this tuple. Whether R dot A equal to S dot A, no. Here, R dot A equal to S dot A, no. So we need not select those tuples. Now, if we consider this fifth tuple in R cross S, so whether 2 is equal to 1, no. Whether 2 is equal to 2, yes. So we need to pick this tuple. Okay. Whether this R dot A is equal to S dot A, yes. Here also it is same. So we need to pick this tuple. This 2 and 3 are not matching, so we need not select this tuple. Right? Now, in this next set of tuples, whether this 3 is equal to 1, no. 3 is equal to 2, no. 3 is equal to 2, no. 3 is equal to 3, yes. So, this is our matching condition, and that is why we need to select this tuple. So, ultimately, in this result, what I'll be having is the tuples, those just we have mentioned. So in this result, we'll be having this tuple, we'll be having these two because they match the values on common attributes. Common attribute here is A, right? So we are having in this relation these tuples. Okay, now what next? Our definition says, so we have done with this. Our definition says that we should pick the attributes those belong to R union S. Right? So we are using projection operation with R union S. So obviously what we need to do is on this result we need to apply the projection operation, right? On this result, we need to apply the projection operation on R union S. So what is R union S here? What is R union S? Yes? What is R union S?
A B C D.
A, B, C, D. Yes. So whenever we use this projection operation, R union S means in our final output, I'll be having A, B, C, D, 4 attributes. So common attribute appears only once. Common attribute appears only once. Right? And what would be the result now? A, B, that will be as it is. C also will be as it is. We are omitting this common column A and this would be our D. Okay. So in my natural join, I'll be having the result like this. So this is my natural join. Okay. And this natural join can be computed by having series of such operations. We are performing R cross S, then we are performing on R cross S, we are imposing the predicate for common attributes using select statement, and further we are using the projection operation to select only the attributes in R union S, right? And ultimately we are getting this result, and this is nothing but our natural join, right? So let us compare now. So see here, this is our natural join result. So these two are the original given relations R and S, and this is our natural join result. So see how this is been computed. 1, 2, 1, right? Common attribute is A. So if there is a match, then that particular tuple gets added. So 1, 2, 1, 4. 1, 2, 1, 4. Okay. Now, what next we are doing? With 1, 2, 1, we are going to match whether any other tuple, this or this, is having the same value 1. No. Right? So we are not going to add anything. Now, if we look at this second tuple, 2, 4, 3. Okay. Now, we are going to match this value of A2 with the value of A in S. So 2 and 1 not matching, 2 and 2 there is a match. So what we have here is 2, 4, 3, 7. 2, 4, 3, 7. Correct? Similarly, if we compare these two, 2, 4, 3 and 2 once again a match. So we need to add this tuple as well. So 2, 4, 3 and D value is 2. So that is being added. Now 2, 4, 3 with this combination A is not matching. So let's forget about that. Now for 3, 5, 1. 3, 5, 1, 1, 4. So 1 and 3 are not matching. 2 and 3 are not matching. 2 and 3 once again are not matching. But only one tuple that matches is 3, 5, 1 along with this 3, 4. So we are having 3, 5, 1 and the D value, that is 4. So this is what our natural join operation is providing us. Got it? Or still any confusion? Yes?
No, ma'am.
Have you understood now?
Yes, ma'am.
So, in this now, you please tell me now, what would be the result of R natural join S in this particular case? Write down the output in your notebook. What would be the output? R natural join S. Yes. See here. We are having this B and D common. B and D common. Okay. So, let us consider this first tuple, alpha 1, alpha A. Right? B and D are common. So what we are going to do next is, we will be searching for the tuples in this relation S such that BD values are 1 and A. So 1A matches with this tuple 1A and this tuple 1A. Correct? So we need to have that combination of tuples. So what we should have? We should have alpha 1, alpha A, alpha, alpha 1, alpha A, gamma. Right? So for this first tuple in R, we'll be having two such combinations because the common attributes are having the matching values 1A. Right? So for this first tuple in R, we'll be having two tuples in our natural join R natural join S. Now for this beta, second tuple, beta 2 gamma A, what are the values of common attributes? 2 and A, BD 2A. So whether we are having any combination 2A here in S for BD values 2A?
No.
No. So we will not have any tuple that matches with 2A here in S. Correct, na? So we will not have any tuple for that. Now for this gamma 4 beta B, gamma 4 beta B. What are the common attributes? B and D. And what are the values? 4B. So whether we are having any matching tuple 4B for BD?
No.
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 So we will not have any additional tuple. Now, for this tuple, what are the values? BD 1A, 1A. So for 1A, we are having two matching tuples, 1A for BD, correct? No? So we need to have two tuples now, alpha 1, gamma A, alpha, alpha 1, gamma A, gamma. Right? Two tuples. So two tuples here we had, two tuples here we had, and what about this final tuple in R? Delta 2 beta B. So what are BD values? 2B. So whether we are having any matching tuple here, 2B for
Yes.
BD? Yes, we
Yes.
have. We
Yes.
have. So we'll be having delta 2 beta B delta. Right? So one tuple. So overall, we'll be having the output like this with 5 tuples. Correct? Any doubts so far? Very important operations, and many times we need to make use of this operation. So try to understand what is happening. Got it?
Yes, ma'am.
May I proceed?
Yes, ma'am.
Okay.
Yes.
Let us see one example of natural join, right, from our university schema. So if I perform natural join of instructor and teachers, if we perform natural join of instructor and teachers, then what will happen? This statement or this natural join will consider only those pairs of tuples where both the tuple from instructor and the tuple from teachers have the same value on the common attribute ID. If you remember the schema, we are having common attribute in these two relations. We have seen this yesterday also. The common attribute in these two relations is the ID, instructor ID. Correct? So if this is the instance of instructor and if this is the instance of teacher's relation, which is the common attribute is this ID. Correct? No? So what we need to do is, or what we will be getting in the natural join is all those tuples from instructor and teacher's relation such that the common attribute ID will have the same value. For example, here I am having this first tuple in instructor table, right? So what is the ID? 10101. So what this natural join will perform, or what this will do is, this will find out all the tuples from teacher's relation wherein the ID value is 10101. So how many tuples are there with ID 10101? 3 tuples. 1, 2 and 3. Correct? So in my natural join, I will be having 3 tuples for ID 10101. Right? So the first tuple will have all those attributes along with these remaining attributes. ID will remain only once. ID will appear only once in natural join. Okay? Because this is the common attribute. So in natural join, for this ID 10101, I am having 3 matching tuples in teachers. So ultimately in my final output, I'll be having 3 tuples for ID 10101. Okay. Now for this 12121, Whether I am having any matching tuple here in teachers for 1 2 1 2 1.
Yes.
Yes. So
Yes.
we will be having that combination 1 2 1 2 1 along with this only tuple. Only one tuple we have, na? So only one record. So 1 5 1 5 1 we are having the match. So we'll be having that tuple as well. For this 2 2 2 2 2 we'll be having a match. So we will have that tuple as well. 3 2 3 4 3 we are having a match, so we'll get that tuple as well. Only the matching tuples, huh? Then 3 3 4 5 6 3 3 4 5 6 we do not have any match, meaning this particular instructor with id 32343 is not, sorry, 33456. The instructor with id 33456, we are not having a match. So the interpretation is like this. This particular instructor with id 33456 is not teaching any subject, any course, right? Because the matching record is not available here in teachers relation. Are you getting me?
Yes, ma'am.
Fine. So
Yes,
this
ma'am.
is how we are going to perform the natural join operation, and whatever we are getting as the output of this natural join is like this, right? So how many attributes we are having? 1 2 3 4 5 6 7 8 instead of 9, right? The common attribute id appears only once. And whatever record, whatever data we are having in this natural join, this is the relevant data only. So if we compare cross product and natural join, cross product is giving us all the pairs, wherein we are having some irrelevant data as well. Whereas in natural join, we are matching the values of the common attributes, and hence whatever is the output of natural join, that is giving us the relevant data. Getting me? Yes?
Yes, ma'am.
Yes,
Fine.
ma'am.
So this is how actually we are going to apply natural join on the real-time databases. Okay, so this natural join, instructor natural join teaches, is equivalent to the relational algebra query written by making use of only the basic operations. So instructor cross teaches, so this is the Cartesian product with the predicate on common attribute, that is id, right? And the outer statement projection operation is simply listing all the attributes, all the unique attributes in both these relations. So simple it is. Please try to understand. So instructor natural join teaches is equivalent to this particular expression. Got it? Any doubt?
Yes, ma'am.
Got it? Or doubt? May I proceed?
Yes,
Yes,
ma'am.
yes, ma'am.
Fine. So now I'm giving you this exercise. Find the names of all instructors together with the course ID of all courses they taught. What we want? You write down this statement. Find the names of all instructors together with the course ID of all courses they taught. Again, see here how I am going to write this. We'll be having the natural join of instructor and teachers, and which attributes we want. We do not want all attributes of this natural join. Simply we want name and course ID. So in project statement we are listing name comma course ID, right? And we are having here the natural join of instructor and teachers. So natural join of instructor and teachers will actually give me this table, this relation, right? So I do not want all the columns. I want only name and course ID. So only these two attributes I would like to extract from the natural join. And that is how we are giving here the statement project name comma course ID instructor natural join teaches. That's all. Got it? Any doubt? Any doubt? Fine. Now I'm going to complete this concept of natural join in next 5 minutes and then we'll conclude. So natural join is associative. So natural join is having the property of association. So what we mean by that? If I'm having the relations like R1, R2, R3, then R1 natural join R2 natural join R3, it's same as first perform natural join of R1 and R2, and whatever is the output of this, perform the natural join of that output with R3. It is same as first perform natural join of R2 and R3 and then perform natural join of R1 and output of R2. Order in which we are computing the natural join of the relations does not matter, right? R1 natural join R2 perform first and then natural join with R3. It's same as perform natural join of R2 and R3 first and then natural join with R1. Both the things are same. This is what the associative property of natural join. Right? Now, one more important property, please understand. If R on R and S on S are the relations on schemas capital R and capital S respectively, and if R intersection S is empty, meaning there is no common attribute in R and S. If there is no common attribute in R and S, then natural join of R and S is same as the Cartesian product of R and S. So this is very important property. If no common attribute in R and S, then both natural join as well as Cartesian product will produce the same result, because there is no common attribute to match. Okay? Got it? Yes? Got it?
Yes, ma'am.
Yes, ma'am.
Fine. Now I am giving you this exercise as homework. Note down the problem statement. Find the names of all instructors in the computer science department together with the course titles of all the courses that the instructors teach. Find the names of all instructors in computer science department together with the course titles of all the courses that the instructors teach. So you should refer to our schema. And which are the relations to be used here to write the query? What you are asked for? Yes. What we want? We want name of the instructor and title of the course taught by that instructor. An instructor should belong to computer science department. Which tables to be used? Which relations to be used? Yes? Where is the instructor name available? In which table? In which table instructor name is available? Yes.
Instructor.
Instructor. So we need to make use of this table. Department name is also available in instructor table. So no worries. We want to list out course title. Where is course title available?
Course table.
Course table. So we need to make use of this. And what we want to list out name of the instructor along with the title of the course that this instructor has taught. So the courses taught by the instructor, this information is available in which table? Instructor along with the courses taught. This information is available in which relation? We are repeatedly using that table to write the queries. Where we have this information about instructor and courses taught. Yes. Teachers. Correct? So this table. So to write this query, I am giving you the hint. To write this query, we need to make use of these three tables. Right? You may use natural join operation to write this query. Okay? So this is your homework. I hope you must have understood the concepts. If there is any confusion, please refer to the videos, those are posted, and clear your doubts. Right? So let us stop today. Next time we'll see the solution for this query. Okay? Fine. So let's conclude. Thank you.